In this tutorial, we'll take a look at the solutions or answers for a test review on exponential and logarithmic functions. So on the first page, there's some multiple choice. And number one, the graph shown is. So we can tell that this is an exponential type curve because of its shape. So really the question is, what's the base? Is it 3, 2, a half, a third, 4? Now, if it's rising, that means that the base has to be a number larger than 1. If it's a fraction between 0 and 1, like the half or the third, then, well, actually that's the kind of shape we have in the second one here. It's actually decreasing instead of increasing as you go from left to right. So is it 3, 2, or 4 is the base? And if you identify a point, and I'm going to use this point right, let's see here. Yeah, that point right there. So the x value there is 2. And so the y value there is 16. So that's the point 2, 16. And there's other points I could have used too. So which of those points is on this curve? And it's actually it's the E one here, because 4 raised to the power 2 gives you 16. So that's why E is the correct answer. If I put 2 in there in place of x, 3 squared would only be 9. Or 2 to the power of 2 would only be 4. So this is the only one that actually contains that point. So it would be the E function, y equals 4 to the power of x. For the second one, the graph shown is, so we're going to take another point again. And I'm going to use, now the correct answer here is C. It's y equals a half to the power of x. And again, I'm going to take a point. So that point right there is the point -2, 4. So again, I would really be checking which curve that's a point on, which curve it satisfies. So if I substitute -2 in place of x here, I get y equals a half to the power of -2. Now remember, a negative exponent means the reciprocal. So this would actually be the same as the reciprocal of a half, which is 2, to the power of +2. And 2 squared works out to 4, which is this y value right here. So that point is on the 1/2 to the power of x. You see, if we put a -2 here in place of x, the reciprocal of a third would be 3, and 3 squared would give you a y value of 9. Okay, so way too big because our y value is only 4. For number 3, the graph of y equals -2 log base 7 of a quarter x has, and logarithmic functions are of this shape. Make a little sketch here. So let's say that's the y-axis, x-axis. Let's draw a logarithmic shape in here. Now, I'm not actually drawing the specific one, but all logarithmic shapes have this kind of a shape. And so they have a vertical asymptote. You know, the vertical asymptote would be, you know, something like that for a logarithmic shape curve. So that's why B is the correct answer for number 3. Now, there's certain transformations here. It doesn't look exactly like that, but it has that shape. So logarithmic graphs always have a vertical asymptote. And as another example, I'm going to bring my calculator over here, my graphing calculator. So, and I'm not going to, well, I guess I could graph that one, but in general, so let's say we're going to graph 4 log x plus 3 or something like that, just to show you that the shape is like this. So it has the same kind of shape. There'd be, for this one, there'd be a vertical asymptote right here. I could actually do that one. To type it in, okay, so we need -2, and my calculator doesn't do log base 7, so what I'd have to do is the log of, and now a quarter is same as 0.25 x, and then divided by the log of 7 because the base is 7. So, okay, so it still has the same general shape. The negative means that it's been reflected in the x-axis, so it's a decreasing instead of increasing curve, but there still would be a vertical asymptote right around here for this graph. for question number 5, write 5 to the power of k equals r in its equivalent logarithmic form. And I always remember how these work by the log form. If you're going from log form back to the equivalent exponential form. And now A is the correct answer here because, you see, now the base of the log, which is 5, is the same as the base of the exponential form. Okay, so base is 5 there. So it goes 5 raised to the power of k is equal to the r, which is exactly what this says. 5 to the power of k equals r. So that's how I always convert from log back to exponential form. For example, this one in B here, the base is k, so that would actually be k raised to the power of 5 equals r. Okay, so that one's actually got the 5 and the k switched, so that's why B is not correct. So A is the correct one for number 4. On to question number 5 now. It says write q equals log n in its equivalent exponential form. Now the base, if you don't see a base, it's automatically 10. So there's actually a 10 here, and it's not incorrect if you write that, but you don't have to if it's 10. So the equivalent exponential form would be 10 raised to the power of q, got my little arrow here, raised to the power of q is equal to n, which is e here. 10 raised to the power of q is equal to n. Last multiple choice, question 6. Logarithmic scales are used when a range of data is, and the correct answer is actually very large. So very small is the opposite. That's not true. The same as the range. I just threw that in for something different, as in range and domain. That's not correct. And so it's not none of these. The very large would be the correct answer for this, but we don't have one of these, so we'll answer none of these for question number 6. On to part number 2, and in the first one we're asked to graph y equals 1.7 to the power of x, and I'm going to bring my graphing calculator back in here, and I'm using a table of values to do this. So actually, let's get rid of that out of that first. So I'm evaluating 1.7 to the power of, and I went from -3 to 5. -3 to 3 would still be okay. So that's where my 0.20435 number would be if I plug in -2 there. Okay, so 0.346, that's where the 0.346 comes from. Now, if you actually have a graphing calculator and you want to produce the table, instead of doing all that, you can actually type in 1.7 to the power of x. Okay, and you see the table function here. So, in fact, I'm going to go to table set, and I'm going to tell it to start -3 and go up by 1. The delta table means it's going in by increments of 1. So actually, if I go table, whoops, I meant second table. Well, I'll let that finish. So second table. So here's my table of values from -3 to 3, and these are the same numbers as over here. Now, if I want to see 4 and 5, I just need to scroll down the table to get to 4 and 5. That's those same numbers there. Now, the inverse, remember, inverses come from switching x and y. So if we switch x and y, y becomes x and x becomes y. It would be x equals 1.7 to the power of y. So that's actually the inverse. And actually, let's move that over here. Whoops. That's actually the inverse on this side. So if I solve for y there, y would equal the logarithm of x base 1.7. Remember, the base of the power is the same as the base of the log. So now you could use either of these for the equation of the inverse. It's normal to use this one because we normally solve for the dependent variable, which is the y. So all I've done for the two tables is switched x and y. So the -3 to 5 x's become the -3 to 5 y's, and these numbers for y become these numbers for x. And so if I plot them, like -3.204 would be that point right there, -2.346 is that point, -1.588 is that point, 0, 1 right there, 1, 1.7 about right there. So I'm actually just plotting those ordered pairs And then I plotted these for the inverse. That's what the inverse would look like. So that's the logarithmic function, that's the exponential function. And again, similar to the multiple choice in the first part, you can see the logarithmic function has a vertical asymptote, the exponential function would have a horizontal one. Question number 2 says evaluate each of the following, showing all steps in reasoning. And for all of these, I'm using the property of logarithms that the logarithm base a of a to the x is equal to x. So as long as the base of the logarithm and the base of that power are the same, that whole logarithm just equals the x exponent. So if I'm going to find the evaluate the logarithm base 5 of 390,625, then I need to write 390,625 as a power of 5. So let's go get my calculator here. Now, you could try powers, 5 to the power of 4. Oh, that's not big enough. 5 to the power of 5. That's not big enough. There is a quick way to do this. In fact, if you take the log of the 390,625 divided by the log base 5, and if you calculate base 5, then you could just do that. So that actually tells me it's 8. So 5 to the power of 8 is that 390,625 number. So I'm changing that into 5 to the power of 8, so the base of the logarithm, base of the power are the same, so it equals the 8 exponent. So that would equal 8. For the second one, log base 2 of 2048, I'd need to write 2048 as a power of 2. And again, I could do, 2 to the power of 7, not big enough. You do a little trial and error if you want. See, 2 to the power of 10 is getting pretty close. 1024, but supposed to be 2048. Oh, I need to go one higher. So you could do that too. It doesn't take too long to get there. So that shows that 2048 is 2 to the 11th. So I can write that as 2 to the 11th, base of the logarithm, base of the power the same. So it equals the exponent of 11. For C here now, the logarithm of this would be, the logarithm base would be 10. So I need to write 0.000000001 as a power of 10. And remember, that's a very small number. If you want to raise a power of 10, you move the digit 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's actually 10 to the power of negative 9. And so it would equal negative 9. For question number 3, we're asked to evaluate logarithm base 8 of 1522 to 4 decimal places. And if you had a calculator base 8, you could just change it to base 8, I suppose. I think there are some newer calculators that actually work that way now, some newer Texas Instrument ones. My older one doesn't. But all you have to do is take the logarithm of 1522, base 10, any base you want, and divide it by the logarithm of the base, and it works out to this 3.5239 number. That's actually the calculation right there. As a check, 8 raised to the power of 3.5239 should equal to 1522. And here's my check here, 8 to the power. Now I've done some rounding. It's not exactly 1522, but it's pretty close. And in fact, if you have a this function here, ln, it's actually pronounced ln. It's actually a logarithm base e, and if you study the calculus, you'll come across the e. It's the number 2.718, etc. And actually, if you use that as well, see, it doesn't matter what base you use, is exactly the same thing. That's another different logarithmic function. So exactly the same thing. In fact, the nice thing about that is if I'm not doing any rounding, I go 18 to the power of that last answer is exactly 1522. So there's a verification that is correct. For question number 4, it says describe the transformations that map y equals log base 5 of x into y equals negative 6 log base 5 of a half x minus 10 plus 3. So there's several different transformations here. So first of all, so there's my answer statement here. The negative 6, so the negative in front here means there's a reflection in the x-axis. The 6 means it's stretched vertically by a factor of 6. See, they're both base 5, so the 5 has nothing to do with what the transformations are, because you're going from one log base 5 function to another log base 5 function. The 1/2 is a horizontal stretch of factor 2. Remember, if the horizontal is a fraction, it's a stretch. If it's a whole number, it's a compression. So it's stretched horizontally by a factor of 2. And the x minus 10 means it's a horizontal translation 10 units to the right. Remember, opposite of that. And then 3 units up. Vertical translation 3 units up. Question number 5, what's the equation of the asymptote for this function? Now this needs to be in a factored form, similar to that was in a factored form. So we have to factor the -3 out of the -3x plus 12. So if I do that, I'll get -3 and then x minus 4. And so the horizontal translation is actually the vertical asymptote. So because it's, see, if there was no translation, the vertical asymptote would be the y-axis, or x equals 0. So because it's been shifted 4 units to the right, then the vertical asymptote equation would be x equals 4. So I paused the video for a moment just to type that equation in. I just wanted to show you what the graph looked like. And again, it's base 2, not base 10. So I would type in 4 log and in brackets. Now I could have put the -3 brackets x minus 4 or -3x plus 12. It wouldn't matter. But I have to divide that by the log of 2 because it's a base 2. And then, of course, the minus 5 in the end. So if I graph it, this is what it looks like. It doesn't have this shape because of the negative here. It's actually reflected in the y-axis. That's why it's going down this way instead of increasing. But see, my scale is 1 here. 1, 2, 3, 4. See, there's 4. So the vertical asymptote would be right here. So that's what the graph would look like. And just a verification that that vertical asymptote is correct. It's always that horizontal translation, actually. Number 6 here says, rewrite each of the following using the power law of logarithms. And it says you do not need to evaluate the logarithm, just use the power law. So log base 4, or 5 to the 6, the power law says that you can rewrite that as bringing the 6 down and multiplying it by the logarithm. So it's 6 times the logarithm base 4 of 5. To do B, I'd need to rewrite the 2187 as, well, as a power. If I could write it as a power other than 3, it wouldn't be a big deal. But because the base is 3, that's why I chose to use 3 here. So 3 to the power of 7 is 2187. And again, you could do a trial and error if you wanted to find that. It's not that big a number. So I can rewrite the 2187 as 3 to the 7th, and then bringing the 7 down in front, it's 7 times the logarithm base 3 of 3. This would be pretty easy to evaluate because the logarithm base 3 of 3, you see the exponent right here is actually a 1. So this would actually equal 1 if you're going to evaluate it. And so 1 times that 7 is 7. So that's another way that law works from earlier in the review. So it would just equal that. The law we were using, of course, said that it equals the exponent. There's the 7 there as well. Question number 7 says solve each of the following. So the first one in A here, 11 equals the logarithm base 3 of x. So I would solve this by just changing it into its equivalent exponential form. 3 raised to the power of 11 equals x. That's the equivalent exponential form. So 3 raised to the power of 11 equals x, or x equals 3 to the 11th. And so I'm actually just evaluating 3 to the power of 11, which is where the 177,147 comes from. In B, 310 equals 7 to the power of 2x. So the x is in the exponent, so I need a logarithm to be able to solve for a variable in the exponent. So to rewrite this in its equivalent logarithmic form, the exponent, 2x, is equal to the logarithm of 310 base 7, which is what this is. Now I'm trying to isolate for x, so if I divide both sides by 2, and that's what's going on here, these 2's divide out, so x is the logarithm base 7 of 310 divided by 2. So that's actually the exact value for x. Now if I want to evaluate that, I could take the log of 310 divided by the log of 7, because 7's the base. And so that's where my 0.29480 number comes from. And then, of course, divide that by 2. So 1.474 is the approximate value for x. We could check that. If we went 7 to the power of, and in brackets, 2 times, now I'm rounding, so it's not going to be exact here, 474, close bracket. I should get pretty close to 310, and I do, 309.99. That's pretty close to 310. If I did the exact calculation here, as I did a moment ago, let's just back up here for a moment. Okay, so there's, and then remember I divided that by 2. So I'm not going to round it all, so I'm going to evaluate 7 to the power of 2 times that number, 7 to the power of 2 times, see the a and s here, my last answer. Lots of calculators have that function. You can just bring that up and it has the exact value for that. So it's exactly 310 with only a rounding. Okay, last page here, 8 and 9. In number 8 it says the difference between sound levels and decibels can be found using the equation, and these are the two decibel readings, B2, beta 2 and beta 1 for the sound, equals 10 times the logarithm of the ratio of their intensities. So again, B2, beta 2 minus beta 1 is the difference in sound levels and decibels, and the ratio of the I's, I1 to I2, is the ratio of their sound intensities. So, and I is actually measured in watts per square meter. We have this formula because of the fact that the range of sounds and their actual intensities in watts per square meter ranges incredibly from a very small, soft sound to a very large sound, like something that's going to cause you pain, like standing 20 meters away from a jet engine. So it says, how many times more intense is the threshold of pain than a soft whisper of 40 decibels? So the 140 and the 40 are the two betas over here, so 140 minus 40. And we're trying to solve for I2 over I1. We want the ratio of their intensities. How many times more intense is one than the other? So 140 minus 40 is 100. And so I divide out the tens. I didn't write that step in here, but I'm actually doing this to get rid of the 10 in front here. So I'm dividing out the tens. And so 100 divided by 10 is 10. It's supposed to be a 0 there, is 10. The tens divide out, so we just have the logarithm on the right of I2 over I1. And so I want to solve for I2 over I1. Remember, the base is 10 here automatically. So there's a 10 there. So I2 over I1 would equal this 10 raised to the power of that 10. Unfortunately, they're both the same number. It kind of looks, it's a little bit confusing because I did make them the same. But yeah, it's this 10, that's the 10 of the base, and that 10 is the exponent in this power. Now 10 to the power of 10 would be a 1 with 10 zeros. So 3, 6, 9, 10 zeros. So that's the ratio of the intensities. The threshold of pain, 140 decibel sound, is 10 billion. Remember, thousands, millions, billions. It's 10 billion times more intense a sound. So that's why it hurts so much more than just a soft whisper. Last question, number 9. The magnitude M of an earthquake is measured using the Richter scale. Again, we have a logarithmic scale because the intensity, the actual amount of power in a low-level earthquake compared to one that would create a tsunami that's of magnitude 8, 9 like that is incredibly large. Okay, so and it's a simpler formula than the previous one. The M is the magnitude, the Richter scale magnitude. It equals the logarithm of the ratio of the intensity of the earthquake to a standard one, or the ratio of 2 earthquakes, like we're going to take a look at. So we can also think of this as like I2 and I1, because we in this case we're looking for how much more intense one earthquake is than another. So the question is, how much more intense was the 1960 Valdivia earthquake in southern Chile? It had a magnitude of 9.5 on the Richter scale. Then the 3.9 magnitude quake on December 17, 1999 near Pickle Lake, Ontario, which is just not too far north, a few hundred kilometers from where I live. And so here's my formula. Again, we want the difference in Richter scale readings would be, I could have written this as M2 minus M1, like I had the beta 2 minus beta 1 over here. So this is the difference between their intensities on the Richter scale. So with 9.5 minus 3.9, this number minus this number, equals the logarithm of the ratio of their intensities. So 9.5 minus 3.9 is 5.6. And again, my logarithm has a base of 10. So I guess this is a little better example here because hard to see my 10 there a little bit. I don't have both numbers as 10. So the I over I naught, or I could have written as I2 and I1, I over I naught is equal to 10 raised to the power of 5.6. And so if I do that, 10 to the power of 5.6 is 398,107. So it's pretty close to 400,000 times more intense. Okay, so that's the more exact answer. I'm rounding here, of course, but it's pretty close to 400,000 times more intense. So that's why it did so much more damage than this earthquake that if you're even 100 kilometers away, you'd feel it move you a little bit, but it's not knocking stuff off the walls or walls down. So that's the end of question number 9 and the end of the test review.